Okay, AP Stats, we are starting Chapter 5, looking at probability in this chapter. The first section is about randomness, probability, and simulation. So it's not a very long section. We have to look at how to interpret probability as a long-run relative frequency and using simulation to model chance behavior. So chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. So what we do is use this rule that's called the law of large numbers. Which says, if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a specific value. So I know this is kind of hard to see, might be a little clearer on your notes packet, but if we're looking at flipping a coin, the proportion of times that we get heads as a result, obviously if we flip only a few times, is going to vary widely. You know, we expect it to be 50% because we know that there are two options. These are things that we know from our early on probability lessons, but if we look at short term, it's not exactly 50% necessarily, a couple times. But if we look at flipping more and more coins many times, then we'll see at the end it eventually approaches that single value of 0.5 that we would expect it to. So the probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. So if we're asked to interpret a probability, we're not going to say the chance of flipping a coin and getting heads is 50%. We would say we would expect 50% of a long series of coin flips to be heads. So let's look at another example of how we would interpret this. According to the Book of Odds website, the probability that a randomly selected U.S. adult eating breakfast is 0.61. So we're not going to say the probability of the next person you find having eaten breakfast is 0.61. We're going to say, if you ask a large number of adults, whether they ate breakfast, or whether they usually eat breakfast, we would expect 61% of them to answer yes. So again, why don't we just say, if we asked 100 U.S. adults, why can't we say that 61 of them eat breakfast? And the reason for that is because it's not going to happen 61 times out of every 100, because every group of 100 U.S. adults, as we know from talking about sampling, every group of 100 is going to vary. So the exact number of breakfast eaters will vary within each sample. Okay. So knowing that probability is a measure of how likely something is to occur, where 0 is impossible, 1 is guaranteed. Let's match all of these. So these are separated by commas here. They got kind of squished weirdly. The outcome is impossible. It can never occur is going to correspond to the probability of 0. The outcome is certain. It will occur on every trial. That would be the 1. This outcome is very unlikely, but it will occur once in a while in a long sequence of trials. So here we are. I would be debating between 1/100th and 3/10. And if I see that this is very unlikely, it's going to lean more towards the 1/100th as opposed to 3/10, because that's not very unlikely. That's not going to happen more often than it is going to happen, but I wouldn't say that it's very unlikely. So I'm going to lean towards the 1/100th as my answer here, because that would occur once in a while in a long sequence of trials. We would expect it to occur once out of every 100 trials. And letter D, this outcome will occur more often than not. So I'm looking here between 6/10 and 99/100. The 6/10 will occur more often than not, definitely more often than not with the 99/100, but that's almost guaranteed. So I think that would have been phrased a little differently. So I'm going to go with the 6/10 here. Okay. The idea of probability seems straightforward. However, there are several myths of chance behavior that we must address. The first one is the myth of short-run regularity. Which is the idea that probability is that randomness is predictable in a long run. Our intuition tells us that random phenomena should also be predictable in the short run, but we cannot use probability to make short-run predictions. So we can't say that 61 out of 100 are going to eat breakfast. That would be more of a short run. And then the law of averages is the other myth, which tells us that random behavior evens out in the long run, but future outcomes are not affected by past behavior. That is, past outcomes do not influence the likelihood of individual outcomes occurring in the future. So what I think about is flipping a coin. Again, I expect about half of them to be heads, about half of them to be tails. So if I flip 10 times and I get heads every single time, the law of averages would say, well, the next one has to be tails because it's got to have to even out. But just because I got heads all those other times doesn't mean I can't get heads the next time. That would be the law of averages. Okay, so a simulation is an imitation of chance behavior based on a model that accurately reflects the situation. Again, that is a simulation because we can't always do the actual experiment. Like if I want to flip a coin 1,000 times, I'm certainly not going to actually flip a coin 1,000 times. So we have to do our 4-step plan here. State, in the case of simulation, we have to ask a question about a chance process. In my plan, I have to describe how I'm going to use a chance device to imitate one repetition of the process, and then say what you're going to record. So again, we're going to describe how to use a chance device There's lots of options. We'll go over a few in a little bit. Chance device to imitate. One repetition of the chance process. Then tell what you are recording from that repetition. Perform many repetitions of your simulation. And conclude your results. To answer the question. So we can use physical devices, like something that they might say for physical devices would be like slips of paper in a hat or something like that. Random numbers, that's table D in the back of your book. And technology, there is a random integer, I don't know what you want to call it. It makes, I can't think of the word, but it makes random integers on your calculator. So that is another thing we can do. So let's try here. We're going to simulate this scenario. In an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of the NASCAR drivers, Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. The company says that each of the 5 cards is equally likely to appear in any box. A NASCAR fan decides to keep buying boxes of cereal until he or she has all 5 drivers' cards. Okay, so if this fan keeps buying boxes until she has all 5, would she be surprised if it takes her 23 boxes to get to the full set? So our problem is, what's the probability that it will take 23 or more boxes to get a full set? So let's go to the next page here to set up our, that was our state really, to state what our issue is. Now we have to plan, do, and conclude. So we have, we need 5 numbers to represent the 5 drivers. First we have Dale, we'll use 1 for Dale Earnhardt Jr. We use 2 for, in order that they were written, I guess 1 would be Jeff Gordon, and then 2 would be Dale Earnhardt Jr. Three is Tony Stewart. Danica Patrick. And 5 is Jimmy Johnson. Oops. Okay, so on our calculators, we are going to use randint, which is going to give me a random integer from 1 to 5. I don't want to set up a whole string of numbers. I don't want to do this like 10 times because I might get it on the first 5. What I want to have happen for each random integer from 1 to 5, that's going to simulate 1 box purchased. Okay. Keep choosing until we get all 5. Okay. So on the next page here we have some room to do a bunch of simulations. So let's go to stat. Oops, we want to do. Okay, so I had to remind myself where this was. So we go to math, over to prob, and randint is number 5 here. We want to select from 1 as my lower limit, 5 as my upper limit, and we're just going to go one at a time because we don't know how many this is going to take. And we're just going to keep hitting enter and recording what we get. Okay, so 5, 1, 3, 3. Let's write those down. Remember, I'm going to stop as soon as I get all 5 numbers. 4, 1, 2. Done. That was fast. So that time 1, 2, 3, 4, 5, I have them all, and that took 8. So let's do that one more time, and then I will write down a couple more examples. Okay, starting over, 5, 2, 4, 5, 2. And then let's keep going. 2, 1, 5, 1. And we just need a 3. So as soon as we see a 3, we can stop. 1, 3. Okay, so that took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so to expedite this process a little bit, I'm just going to write down a couple more number sets. Do this as many times as you want to, or as many times as it says to. This next set, 3, 5, 2, 1, 5, 2, 3, 5, 4. That took 9 boxes. 5, 5, 5, 2, 4, 1, 2, 1, 5, 3. That took 10 boxes. Let's do one more so we have an even 5. 4, 3, 5, 3, 5, 1, 1, 1, 5, 3, 1, 5, 4, 5, 2. That was 15. So now to calculate the actual probability, each of these times was a simulation of purchasing cereal boxes until we got all 5 numbers. So the question is, what's the probability that it's gonna take 23 boxes? So what I'm looking at is, of my examples here, how many times did it take 23 boxes? And it did not take 23 any of our attempts. So 0 out of 5 trials. So we would expect the probability to be 0. So there's our math, but we can say the probability based on our trials of needing to buy 23 boxes to get a full set was 0. The NASCAR fan should be surprised that it took her so many. Okay, so now looking at a little adjustment on this one. So we still are looking at the similar example, but this time instead of each one being equally likely to be chosen, how would we adjust this if we had certain percentages for each driver? So if we know that Jeff Gordon was in 10% of the boxes, Dale Earnhardt Jr. in 30, Tony Stewart in 20, Danica Patrick 25, and Jimmy Johnson 15, how would we modify the simulation to estimate the chance that a fan would have to buy 23 or more? So here, instead of doing 1, 2, 3, 4, 5, we have to have a range of values. So Jeff would be, instead of just one digit, he would be, let's see, we have to be in, if we have, this is all in percents, we want to do 100%. Anytime you have anything in percent, it would be a really good idea to do. Okay, so like I mentioned, when you have 100% total, instead of having to do everything as 3 digits, like if we're looking at the random number table or something, remember that you always have to go by that number of digits. So if we're doing 100, then it's easier to do 0 through 99. which is technically 100 numbers, but that way you don't have to go out all the way 3 digits. If you're on your calculator, it doesn't matter, and you could do 1 through 100, but if you just start sticking with 0 through 99, then you just get used to that, and it's standard when you have to use 2 digits for the table. So we would do 0 through 9 for Jeff. Dale, we'll just do first names here. Dale, we would do 10 through 39 since he has 30%. Tony, add 20% to that, starting at 40, would end up going to 59. And again, remember that if we counted every single one of those digits, there are in fact 20 digits there. Then Danica would be 60 through 84. And Jimmy would be 85 through 99. Okay, so instead of doing all of those simulations, let's just do one simulation and see how much longer it takes. We want one from each set. So we'll have to adjust our settings here. We'll want that, want that to be random integer, we want to do the one with the settings so that we can adjust it. Random integer from 0 to 99. We want one at a time. 85, 97, 27, 27, wow, and 12. Let's write those down. So I'm going to cross these off as we can get them here. So we got Jimmy covered, we got Dale covered 3 times, and Jimmy covered twice. So we need some different numbers here. Let's clear those out, keep going. 5, 72, 1, 42. Let's see where we're at. Okay, so the 5 is here, 72 is here, 1 was back here, and 42 was here, so we just got them all. Good timing to stop. So that time it took us, that's 9. That is actually about the same as it took last time, which is very surprising because when they are so restricted, I don't think it would be as unreasonable to expect it to take 23 or more boxes. So if we kept going, we could see how many times it took us 23 and then divide by our number of trials. And that is the section, learning how to simulate, interpret long run relative frequency, and then our simulating chance behavior using the calculator. But remember that we are also going to be expected to use a random integer table, the random number table, and we go by sets of that many digits. So if we were to have done this question with the random number table, we would be looking at 2 digits in a row, and we would look for how many digits it would take for us to get 1 in each of those categories. That is our section 5.1 on basic probability.